In the silent, frozen forests of Lapland, inside the waterlogged timber of ancient French riverbeds, and within the sacred cedar groves of Japan, a secret history of our sun has been hiding for millennia. For generations, we believed the sun to be a constant, benevolent yellow dwarf, a steady heartbeat sustaining life on Earth. We knew it could occasionally tantrum, sending auroras dancing across the polar skies, but we assumed its rage had limits. We were wrong. In 2012, a young Japanese physicist named Fusa Miyake peered into the atomic structure of a 900-year-old cedar tree and found something that should NT exist, a radioactive scar so massive, it suggested that Earth had once been struck by a cosmic storm of apocalyptic proportions. Since then, scientists have uncovered more of these Miyake events, invisible, cataclysmic explosions that have pummeled our planet repeatedly over the last 15,000 years. These are not merely scientific curiosities, they are warnings. They tell us that the worst-case scenario for space weather is not the famous Carrington Event of 1859, which set telegraph wires on fire. The worst-case scenario is something far darker, a storm thousands of times more powerful that, if it were to strike today, would send modern technological civilization back to the Dark Ages in a matter of hours. This is the story of the Miyake Events, how we found them, what caused them, and why they might be the greatest natural threat we are currently ignoring. To understand a Miyake event, one must first understand the exquisite recording device that nature has provided us, the tree. Every year, trees add a new ring to their trunks, a layer of growth that acts as a precise calendar. But these rings capture more than just rainfall and temperature, they capture the chemistry of the atmosphere itself. High above our heads, at the edge of space, cosmic rays, high-energy protons from exploding stars and galactic cores, constantly bombard Earth. When these protons slam into nitrogen atoms in our upper atmosphere, they trigger a nuclear reaction that creates carbon-14, or radiocarbon. Carbon-14 is radioactive and unstable. It drifts down from the stratosphere, oxidizes into carbon dioxide, and is inhaled by trees during photosynthesis. Once the tree ring is formed, that carbon is locked in place forever. By measuring the ratio of carbon-14 to stable carbon in a specific ring, scientists can determine exactly how much cosmic radiation the Earth was receiving in that specific year. For decades, radiocarbon scientists assumed this background radiation was relatively stable, fluctuating gently with the sun's 11-year magnetic cycle. When the sun is active during a solar maximum, its magnetic field shields Earth from galactic cosmic rays, lowering carbon-14 levels. When the sun is quiet, more cosmic rays get in, raising carbon-14. But in 2012, Fusa Miyake, a graduate student at Nagoya University, decided to look at the data with higher resolution than anyone before her. She examined the rings of a Japanese cedar dating back to the 8th century. What she found defied the standard model. In the wood corresponding to the years 774 and 775 AD, the levels of carbon-14 didn't just fluctuate, they skyrocketed. The data showed a 12% jump in a single year, a spike 20 times larger than anything caused by normal background cosmic rays. It was an impossible surge. For the entire planet's atmosphere to change that drastically in 1 year, something extraterrestrial must have hit the Earth with the energy of thousands of nuclear bombs. Miyake published her findings in Nature, sending shockwaves through the astrophysics and archaeology communities. Skeptics initially scrambled for earthly explanations, perhaps a local supernova or a measurement error. But soon, other laboratories across the world checked their own ancient wood samples. From German oaks to New Zealand kauris, the signal was there. The entire planet had been irradiated simultaneously in 774 AD. The Miyake event was born, and the hunt for more began. Once scientists knew what to look for, the trees began to speak. Over the last decade, researchers have combed through dendrochronological archives and ice cores, which store similar cosmic spikes in the form of beryllium-10 and chlorine-36, to construct a timeline of these invisible disasters. The list is growing, and each date represents a moment when the sky effectively fell. The first discovered event, the Charlemagne spike of 774 AD, remains one of the strongest of the historical era. Occurring during the reign of Charlemagne in Europe and the Tang dynasty in China, this event bombarded Earth with enough high-energy particles to cause auroras that would have been visible practically at the equator. An entry in the Anglo-Saxon Chronicle for the year 774 describes a red crucifix appearing in the heavens after sunset. While often dismissed as a halo effect or metaphor, in light of the radiocarbon data, this may be an eyewitness account of a blood-red aurora borealis twisting overhead in skies where such sights were impossible, signaling the radiation storm raining down from space. The second confirmed event, found shortly after the first, occurred in 993 AD. While slightly weaker than the 774 event, the 993 spike proved to be a revolutionary tool for historians. For decades, archaeologists knew Vikings had reached North America, settling in Newfoundland, Canada. but they couldn't pinpoint exactly when. In 2021, researchers analyzed wood chips left behind by Viking carpenters at the Lance Awe Meadows site. They found the 993 AD carbon-14 spike in a specific ring. By counting the rings from the spike to the bark, the year the tree was felled, they determined the Vikings cut down those trees in 1021 AD. The Miyake Event turned a vague archaeological theory into a precise historical fact. Moving back into the Iron Age, another event struck in 660 BC during the rise of the Neo-Assyrian Empire. Like the others, it is confirmed by ice cores from Greenland and Antarctica. Even further back, in 5259 BC, a Neolithic pulse occurred, which researchers in 2024 used to pinpoint the dating of the Despilio prehistoric settlement in Greece. This event occurred over 7,000 years ago, yet the signal is as clear as a bell in the fossilized wood. Perhaps most disturbing to astrophysicists is the event from 7176 BC. Usually, solar storms occur during solar maximum, the chaotic peak of the sun's 11-year cycle. However, when researchers analyzed the 7176 BC event, traces of other isotopes suggested the sun was actually in a quiet phase, a solar minimum. If a Miyake event can occur when the sun is sleeping, it suggests our star possesses an explosive mechanism we do not yet understand. It implies there is no safe time. But the most terrifying discovery came recently, in late 2023. A team led by Edouard Bard and Tim Heaton analyzing subfossilized trees eroding out of the banks of the Druzé River in the French Alps found a spike that dwarfed the others. Dated to approximately 12350 BC, roughly 1,300 years ago, this event was roughly twice as powerful as the 774 AD event and an order of magnitude stronger than anything else on record. To put this in perspective, the Carrington Event of 1859 is estimated to have released roughly 10 to the power of 32 ergs of energy. The 14,300-year-old event likely released energy in the realm of 10 to the power of 35 or 36 ergs. If the Carrington Event was a hand grenade, the French Alps event was a tactical nuke. So what in the universe is capable of doing this? When Fusa Miyake first published her paper, the scientific community cast a wide net. Was it a gamma-ray burst from a dying star in a distant galaxy? Was it a nearby supernova? Or perhaps a magnetar flare? Slowly, the evidence has eliminated the exotic suspects. If it were a supernova, we would likely see the remnant nebula in the sky today, and the event would be accompanied by other isotopes that are missing from the record. A gamma-ray burst would be a hard pulse, short and sharp. But some Miyake events show a tail of radiation lasting a year or two, suggesting a prolonged bombardment. The consensus has settled on the most frightening culprit of all, the sun. It appears our sun is capable of producing superflares, magnetic explosions thousands of times more powerful than anything observed in the modern era. We have seen these superflares on other stars that look like the sun via the Kepler Space Telescope. For years, astronomers hoped those other stars were just younger or faster rotating versions of the sun. They hoped our middle-aged, sedate sun had grown out of such violent behavior. The tree rings prove otherwise. The sun is not a steady candle, it is a dormant volcano. The mechanism is likely a massive short circuit of the solar magnetic field. A coronal mass ejection, a billion-ton cloud of plasma, is hurled directly at Earth. When this plasma cloud slams into Earth's magnetic shield, the magnetosphere, it compresses it, dumping trillions of watts of energy into our atmosphere and creating a particle shower of neutrons and protons that rains down to the surface. But the Miyake events present a solar paradox. Standard solar physics models struggle to explain how the sun can store enough magnetic energy to release a flare of the magnitude seen in 7176 BC or 12350 BC. We are missing a piece of the puzzle regarding how our own star functions. Why does this matter? We survived 774 AD. We survived 993 AD. Humanity marched on. But the humanity of 774 AD was made of wood, stone, and iron. The humanity of the 21st century is made of silicon, copper, and fiber optics. We have built a civilization that hangs by a thread of copper wire. Our entire economic, social, and logistical existence depends on the flow of electricity and the integrity of data. A Miyake event is specifically designed by nature to destroy exactly that. If the 774 AD event were to happen tomorrow, we would face a sequence of events leading to an internet apocalypse. It would start at minute zero. Light travels at 186,000 miles per second. The X-rays and UV radiation from the superflare would hit Earth 8 minutes after leaving the sun. They would instantly ionize the upper atmosphere, causing a global radio blackout. GPS would degrade immediately. But the real danger is the plasma cloud, traveling slower, arriving 12 to 24 hours later. Around hour 12, the impact occurs. When the particle storm hits, Earth's magnetic field would ring like a struck bell. This induces geomagnetically induced currents, or GICs, in the ground. These currents seek the path of least resistance, our long-distance power transmission lines. This leads to the transformer killshot. Modern high-voltage transformers are the backbone of the grid. They are massive, custom-built beasts, often weighing hundreds of tons. The excess current from the solar storm would overheat their cores, melting the copper windings and causing them to explode or fuse permanently. In 1989, a tiny solar storm knocked out the Quebec power grid in 90 seconds. A Miyake event would not just trip breakers, it would physically destroy the hardware. The problem is that we do not have spare transformers. They are custom manufactured, often taking 12 to 18 months to build. If a Miyake event destroys 50% of the transformers in North America and Europe, there is no factory power to build new ones, and no road network functioning to deliver them. We would be looking at a blackout not of days, but of years. Then there is the undersea Achilles heel. For a long time it was thought fiber optic cables were safe because glass doesn't conduct electricity. But the repeaters, the amplifiers placed every 50 to 100 kilometers along the ocean floor to boost the signal, are powered by a copper conductor running alongside the fiber. Research presented in 2021 by Sangeeta Abdujyothi highlighted that these repeaters are highly vulnerable to GICs. A Miyake event could fry the repeaters on transatlantic and trans-Pacific cables, while the internet might survive locally, allowing you to send an email from New York to Chicago. The World Wide Web would be severed. Europe would disconnect from America. Asia would go dark. The global financial system, which relies on millisecond timing transactions across oceans, would evaporate instantly. Above us, the satellite graveyard would form. Thousands of satellites would face immediate death. The radiation would fry their solar panels and logic boards. But worse, the massive dump of energy into the atmosphere would cause the atmosphere to heat up and expand, puffing out into space. This increases drag on satellites in low Earth orbit, including the space station, and massive constellations like Starlink. They would lose momentum and fall out of orbit, burning up in the atmosphere. We would lose GPS, weather forecasting, and satellite communications in a single afternoon. Furthermore, the 774 AD event depleted the ozone layer. A modern simulation suggests a strong Miyake event could destroy up to 8.5% of the ozone layer and keep it depleted for years. This would allow intense UV radiation to hit the surface, damaging crops, causing widespread skin cancer, and altering global weather patterns by cooling the poles and shifting the jet streams. There's a concept in the search for extraterrestrial intelligence called the Great Filter, a hurdle that prevents civilizations from becoming spacefaring. Some argue that nuclear war is the filter. Others say it's climate change. But perhaps the filter is the star itself. We have built a civilization that is hypersensitive to the mood swings of its host star. We did this during a period of unusual solar calm. The last 100 years of high-tech expansion coincided with a lack of Miyake events. We have been lucky. But the tree rings tell us that this luck is a statistical anomaly. The average interval between confirmed Miyake events is roughly 400 to 400 years. It has been over 1,000 years since the last major one, in 993 AD. We are, by many measures, overdue. Is there any hope? Yes. Now that we know Miyake events exist, engineers are beginning to take notice. Power companies are exploring capacitors that can block the DC currents induced by solar storms, protecting the transformers. Engineers are looking at radiation-hardened electronics for satellites that can withstand a 774 class event. And artificial intelligence is being trained on solar wind data to give us better prediction models. If we have 18 hours warning, we can shut down the grid intentionally. A cold grid is much harder to melt than a live one. We can ground flights and reorient satellites. The discovery of Miyake events is a triumph of interdisciplinary science. It took a Japanese physicist, French geologists, American archaeologists, and polar researchers to piece together the puzzle. When we walk through a forest today, we are walking through a library of cosmic catastrophes. The trees have been trying to tell us for centuries that the sky is not safe. The rings inside the trunk of a grand old oak or a scrubby Lapland pine are not just counting years, they are counting the beats of a chaotic, dangerous star. We cannot stop the sun from exploding. The physics of a G-type star are beyond our control. But we can choose how we read the history it has written for us. We can ignore the warnings in the wood and continue to build a fragile, interconnected world that sits unknowingly on the chopping block. Or we can listen to the trees, respect the ferocity of our star, and build a civilization resilient enough to weather the storm when, not if, it comes again. The next Miyake event is out there, written in the future, just as clearly as the last one was written in the past. The only question is whether we will be reading the data on a computer screen or by the light of a fire.